Hello. All right, welcome back to Physics 112. Today is the first lecture for exam 3. Oh, exam 4, sorry. Let me change the battery brightness, meaning like the auto off brightness. Never. Okay, good. So I push an iClicker question, and 101 of you have answered. What is the answer of this question? You. Yes, you. You promised to participate, right? Yeah. Light. Interesting. It's 1/3 of the answer. So we discussed last time. It's Fermat's principle of least time. So basically, with Fermat's principle of least time, you can derive, if you have to, let's say you have to restart civilization and stranded in deserted island, you can derive all the equations in optics, in ray optics, using Fermat's principle of least time. Okay. Some of you like the mind map that I made for exam 3. So I made one for exam 4. It doesn't look like this. It looks much nicer than the one that I'm showing you. But this one, basically what we are doing today, we will do refraction, dispersion, total internal reflection. And if we have time, we will do rainbow. Okay. Some of you may ask about exam 4. The average is 80%. Can we? So the average is 80%. So because of that, there is no extra credits. Some of you asked me about projected grade. I can send projected grade to you in an hour or so. But it's a forecast. That means many assumptions. And depending, the assumptions is you perform as you currently perform. Let's say you still go to recitation, you still participate in iClicker. If you do that, then the projected grade will be somewhat accurate. So one of the assumptions is that your recitation grade is either 0%, 50%, or 100%. So I will give you those three because I don't have the grade for your recitation yet. The final exam is basically the mean of your 3 exams. The exam is the mean of your 3 exams because we don't have 4 exams yet. I cannot drop the lowest one. Yeah. Oh, there is no curve in this class. Oh, yeah. You will see. It will be after I add the extra point. Do you want me to curve the class or no? Because right now, based on the projected grade, assuming that all of you get 100% recitation, half of the class gets A minus, A or A plus. Half of the class get 85%. If you want me to curve it, 1/3 of the class will get A minus or better. So it's up to you. Right? I don't want you to send email to Joe Biden like, hey, my professor is an idiot. He doesn't know how to curve. Yeah. A minus is 85%. And typically what I do is maximum grade turns out to be 107 in this class. And then I split equally, unbiased. So 85 to 107, I split into 3, A minus, A, and A plus. So instead of tweaking things here and there, I just do it blindly. Okay, but 85% is an A. I think 75, it's on the syllabus. You can read it on the syllabus. So that's one. And then we will have class. Oh, one question is that some of you asked me about if you're happy with the grades, whether you should take final and exam 4. You don't have to, but I highly encourage you to do that. Okay, and it will not hurt your grades. If you skip those exams, ASU will still not refund your tuition. You cannot get 25% refund if you skip 25% of this class. So you already pay for it, make the most of it. Okay. Okay. Yeah, Ashley, and then we should continue. If you are happy with your grade, yeah, because final basically covers exam 1, 2, 3, 4. So they test the same thing. All I care is I want to assess your understanding. That's the last question. We have to continue. Yeah. Yeah, I mean, it's really easy with computer code. It's really easy to find which one is bigger. So everything will be handled, and you will have all the details in the weekly grade updates. Some of you may not like it because it's too much information, but it's my way to be fully transparent. And I'll be happy to answer or to spend 5 minutes in Friday's lecture to answer your questions, but we have to continue. Okay. Next is the course organization. We are right now in lecture 25. I will not be, so good news, I will not be in the class on Wednesday. Ross, our TA, will substitute for me, and I'm sure he will do a better job than me. So Ross, and then exam 4 is on the 22nd, and final exam is on the 29th. And then I think I have to submit your grade a week after the final exam. I'll try to put the grade early enough so we can, if I made a mistake or if you want to negotiate, there will be plenty of time to do that. Okay, so Fermat's, what is Fermat's principle of least time? Anyone still remember? Fermat's, yeah, Dinesh. Yeah, sorry, I know you're not Dinesh, I'm just, didn't have enough sleep. Yeah, light travels along the path that takes the least amount of time. So one example is this laser here, which doesn't work. So basically, light travels, if we have 2 points, we know that light travels along a straight line because a straight line takes least amount of time. Okay, first speed of light is c, right? And then this one is not accurate because this one speed of light in vacuum or in air for this class. So even if you travel with a constant, with the same speed, the shortest path will take the least amount of time. So and then before exam 3, what we did is we show that if we have 2 points, A and B, but the rule is the light has to touch a surface before once between point A and point B. Turns out that the path that takes the least amount of time is when the angle of incidence is equal to the angle of reflection. We did this last Monday. No, Wednesday. Wait, I think Monday. Okay. So right now so far we study that light travels in one medium. So what happened when light travels from medium 1 to medium 2? So let's say light travels from medium 1. You need to help me. Medium 1 to medium 2. One example that all of you have ran experiments in your lifetime is from, let's say, air to water. It turns out that something changed. One is the density of the material changed. For example, if this is water, then water is more dense than air. And because of the propagation of electromagnetic waves in material, the wave interact with materials, turns out that the speed change. Here, the speed of light is c. Here, the speed of light in a medium is c. Is smaller than speed of light because it's more dense. And we have a constant that is a property of material. So here, the name of the constant, the symbol is n. So n is refractive index or index of refraction. I use refractive index. So this is the definition of a refractive index, the speed of lights in so the speed of light in vacuum divided by n is equal to the speed of light in a material. Or if you want n to be on the left-hand side, n is equal to c divided by v. And there are some common materials. So vacuum, n is equal to, let's just do this, and vacuum is equal to 1, and water is equal to 1.33, and the refractive index of glass is 1.5. The reason why we like these materials because many pre-meds you care about biological systems, so water is important, and glass because many optical components are made of glass. Okay. So the speed change, how about the frequency? Frequency doesn't change. Okay. So from exam 3, we know C is equal to lambda times frequency times F. So this is in vacuum. So in a medium, C becomes V because C is reserved for the speed of light. And then lambda in vacuum divided by N. So maybe I can use vacuum here. And then times frequency. So frequency stays the same, but the lambda changes. Is that right? Okay, good. Any question? So this one typically appears on the exam. Could appear on MCAT also, that the wavelength changes, but the frequency stays the same. So I have this famous iClicker question for you. So this question has something to do with Fermat's principle of time, but this is typically written in different ways, and I haven't thought much about this. So let's say you want to go from, let's say you are a fan of, I don't know, can reveal my age, like Metallica, let's say. Metallica is on the beach. What do you guys listen to? Justin Bieber? Justin Bieber is too old for you. So let's say Metallica is here, and there is an old physics professor here, and this person wants to get Metallica's signatures. And then there are many crowds. Some of them took physics 112. Some of them didn't take physics 112. So the question is, if this physics professor wants to get the signature as fast as like if he wants to beat other crowds, which path that he should take? Okay. So first, I haven't set up the problem carefully. This one is a parking lot. In parking lot, we can run faster than on a sandy beach. Right. So the question is whether he minimize the distance in the parking lot or minimize the distance on the sandy beach, or he should just use the path with the shortest distance. So that's the iClicker question. So, can you say it or no? All right, so almost all of you have answered. 5 more seconds. 3, 2, 1. You guys are fast this year. Oh, by the way, I have, as a typical Asian parent, I need to give you compliments. You guys are really fast this year. Last year, every iClicker was 2 minutes. And one of them complained to the dean because I only assigned 2 minutes. And on top of that, you guys, this cohort has the most A's. I can see that. So sorry to distract, but sorry for the disruption. But okay, so let me reveal your votes. Okay, it's actually not a bad guess. So some of you think that we should minimize the distance on a sandy beach, which is not a bad guess. And some of you, 18% of you, thinks that we should just ignore the speed on the path or on a track. So choose B. Turns out that when you do the math, the right answer is C. Okay, so it's a combination of both. Because you can run faster on an asphalt road, then you want this path to be longer. But if you take it to the max, turns out that the total distance is too much. So in a way, this is what light does when you, let's say, dip your pencil in a transparent cup. The pencil will look bent because light decides to travel along the path that takes the least amount of time. And on the exam, I may put another asphalt here. Let's see, I can and ask you what is the path. So just to give you some, if there is another asphalt here, then it will be like that. So this one will be parallel to the orange line. Any question? Good. So the answer is C. But mathematically, there is a there is a formula. So okay, so let me translate the. Let me first grade the answer. So let me translate that to optics. So if light travels from medium 1 to medium 2, okay, medium 1, and medium 1 doesn't have to be air, okay, and medium 2 at an angle. First, at an angle doesn't mean anything. Angle means the angle between two lines. So we define what we call normal line. And normal, we have encountered this language before in math and in physics. Normal means it's perpendicular. So normal line. The exact term doesn't really matter in this class. You can call it normal axis. Fine. And let me exaggerate the angle a little bit. And then let's say like a pencil, it bends closer to the normal. And then the angle is, we call this angle here is angle of incidence or incident angle. This is angle of refraction. Okay. Or if you want to make it generic, we can call it I and J, meaning 1 and 2. It doesn't have to be 2. There could be another material here. And it doesn't have to be two different states. It can be hot air. It can be cold air. It can be oil. It can be water. Okay. So the formula is given on the slide, which is N1. Did I use 1? Good. Times sine theta 1. This is 1, not I. Is equal to N2 times sine theta 2. Okay. So the refractive index of medium 1 is N1. The refractive index of medium 2 is equal to N2. Okay. How do we know that this equation is correct? Because it's on the slide. So let's say N1 and N2 is the same. That's one way to prove or like to convince yourself that I didn't make a typo. Let's say N1 and N2 is the same. That means there is no medium change, and the light will travel along a straight line. Then if N1 and N2 is the same, then theta 1 is theta, and theta 2 is the same. So that's one way to test or to solidify your understanding. Okay. And there is this simulation. Let me first get that simulation. Maybe. Sorry, apologize. George. Okay. So there is the simulation that, if you haven't played with simulation, optics is probably the best subfield of physics to simulate because it's really visual. So some of you may not like electromagnetics because it requires imagination, but optics is something that you see. So let's say for the simulation, you can change the angle, the incident angle, let's say to 45, and you can also change here from air to glass. And I want you to ignore one thing. I want you to ignore the reflected beam because we haven't studied about reflection. Turns out that when light travel between two medium, there is always reflection. And based on N1, N2, you can easily solve for the angle. And the angle will look like that. And then the angle is a function of the difference of the refractive index. So let's say if the refractive index is the same, there is no bending of light. and this one. And you can derive that Snell's law using Fermat's principle of phase-time. I think most books for pre-meds use Huygens principle. That's something that we don't cover in the class because I think Fermat's principle of phase-time is far more powerful. But you should learn about Huygens principle by yourself. Any question? Okay. We have an iClicker question here. Do you want to do iClicker or you want to go straight? So here is a simple question using Snell's law. Basically, first, one principle that we learned on Monday, last Monday, was Fermat's principle of least time, or light is lazy. Second is principle of reciprocity, meaning this angle is always correct, or always the angles are the same whether you go from medium 1 to medium 2 or the opposite from medium 2 to medium 1. Okay, so don't worry about the arrow of the light path. So the question here, so maybe there is a fish here and the angle of incident is 30 degrees. The question is, what is the angle of refraction? And I forget to make the option, but that's so you can put the number. The unit is in degree. Okay. And we can spend 2 minutes for this problem. Okay, 30 more seconds. Yeah. What is the significant digit? Don't worry about it. I'll grade it manually. All right, 10 more seconds. Basically, all of you have answered. 5 more seconds. 3, 2, 1. Okay, so I don't think I need to do it for you, or maybe I should. So that's the answer. So you use this formula. So N1 times sine 1 or sine theta 1 is equal to N2 sine theta 2. First, you should know that this function, the sinusoidal function, is bounded between -1 to 1. So if you get more than 1 and you try to find the angle, then you don't get a real number. There is a number, but they're not real. They are real, but they're imaginary. So and 1 is 4/3. Sine 30 degrees is 1/2. And 2 is 1, then sine theta 2 is sine of theta 2. This one is 2/3, so sine of theta 2 is 2/3, and you can use your calculator to get theta 2, okay, which is 41.7, which is, okay, so most of you got it right. And I'll grade this later after the class. Any questions, Sophia? Yeah, so that's a good question for the next iClicker question. So, and we didn't coordinate, by the way. So the question is, this is spearfishing. I showed this picture on Monday. It wasn't that picture, it wasn't my son. I think I know how he looks. I work a little bit too much. So Sophia asked, so if there is a fish, and if we see a fish, let's say again, if you're stuck in a deserted island and you need to restart a civilization, physics 112 will be useful because you can catch fish. So a fish swims below the surface of the water at P. An observer at O sees the fish at deeper than the fish or the same depth or smaller depth than the fish really is. Okay, so let me send you. So let's spend 30 seconds for this iClicker question. All right, 5 more seconds. 3, 2, 1. Okay, good. So it seems that, okay, can anyone help me why the answer is shallower than the position of the fish? Anyone wants to help me? 76% of you. People at the back. Wait, so how did you answer? It was like, if you answer randomly, the percentage should be 33%, but obviously it wasn't random. Yeah. What's your name? Ah, I see. Aha. Okay. Excellent. So this, all of you probably know right now, I'm more conceptual. Physics students say I'm really philosophical. I think it's an insult. Basically what they are saying is, I don't know how to do math. But here is a little bit philosophical. It turns out that when we see actually in our brain, right? Our brain process, and we know that because there was an experiment where the students, I assume, or patients were given glasses that flip the image. Initially, they get confused, but after a few days, they can function properly because you just need to do a flip operation in your brain. So this is the answer. So basically, fish can bounce lights towards all direction, not just 3, but this is basically many direction. Okay, so if I draw all the lights, then it will be all black. And then if the angle of incident is this one, the one that I'm highlighting right now, then the angle of refraction will be the one that I'm highlighting right now. Similarly for the other 2, okay? And so we get this lights. And then turns out that when we image, because we don't interrogate every photons or every lights, we don't know whether the light was refracted or bounce a mirror or anything. What our brain does is we extrapolate. So we extrapolate all these lights. And then when we do that, the fish will appear along the y-axis. It's the same x, meaning same x-axis, but along the y-axis, it's shallower. So this is because our brain make a projection or extrapolation. Any question? Okay, and this may appear on on MCAT. I don't even notice this. This is my way to get your attention. So this question may appear on MCAT, which is another question, which probably we shouldn't do iClicker. A fish swims below the surface of the water. Suppose an observer is looking at the fish from point O prime, straight above the fish. The observer sees the fish at, do you want to do iClicker or no? Okay, let's do iClicker then. Okay, let's spend, last time we spent 45 seconds. All right, 10 more seconds. Five more seconds. 3, 2, 1. Okay, so what's the answer? The answer is? So it's the same thing. Basically, again, it may show up on MCAT, sorry. I don't know much about MCAT. So when I say it will show up on MCAT, you should translate that, that claim to please pay attention. So basically, again, this fish will bounce lights towards all direction, right? And when it bounce light horizontally, of course, it doesn't travel between different medium, but when it travel vertically or somewhat vertically, there is refraction. And again, the way our eyes work is we make projection. And then if you extend all these lines, it will intersect at point P prime, which is shallower than the fish is. Okay. So the answer is C. Okay, good. Any question? Yeah, okay, you Max. Ah, it's a good question. Thank you. So the light doesn't travel perfectly at 0 degree. You know, your eyes is not infinitely small object. Right? There is angle right there. This is an exaggeration, of course. Otherwise, the drawing is very tight. So there is angle, there is still angle there. Just imagine, let's say if your eyes is this big, maybe. Good question. Okay. Now we move to the next topic, which is total internal reflection. This is very near and dear to my heart. And this is really important in many technologies, including Alex. You should stay for 1 minute. No, you can stay there. This is actually involved in DNA sequencing. I know you do DNA sequencing all the time. but not with Oxford nanopore, but this is with Illumina technology. So we know that we can vary the angle. And then when we vary the angle, we also vary the refracted beam. One thing that is interesting, if we go from, well, we can just swap the refractive index from glass, let's say, to water. The reason why I say glass and water, because it's a classic system. When we do microscopy, when we image, basically we image through glass, which is the objective lenses, and water, your biological sample, right? So it turns out that if you travel from more dense to less dense medium, there will be a line where all lights gets reflected. Okay, so right now some of them are reflected, some of them are refracted. But when it reach critical angle, all of them are reflected. Can you see? Is that clear or no? Fabian, is that clear? So smaller than critical angle, there is still refraction. Critical angle, and then larger than critical angle, all of the lights gets reflected. Okay. So why this is important? Not because I want you to come back. Don't. That's the wrong answer. Let's say this is important because turns out, so we know that when electromagnetic wave travel, it carries energy. So we have energy, and there is no electromagnetic wave here. So you may think that there is no energy here, but it turns out that nature doesn't like sharp transition between high energy electromagnetic wave and zero energy. That doesn't happen in nature. So there is a little bit electromagnetic energy. The name is evanescent wave. And in sequencing technology, what we use, what Illumina use, which is probably like $50 billion company by now, is they put the DNA that they sequence here. The reason why this is nice, because they want, it is a way to excite or to probe sample that is near surface without perturbing sample that are far from the surface. We need that to minimize noise. If electromagnetic wave like goes through like this, then you will get noise or background signal from samples that are in solution. Okay, now you can go. Sorry. So this is the name is evanescent wave. It's useful in many technologies. In my lab, we benefit from evanescent wave all the time. One of the king of evanescent wave is Taekjip Ha. He is the president of Biophysical Society meeting. I will invite him. I will be hosting him next Thursday. So he will give a seminar in this building on Thursday. He's at Harvard University. Okay. So total internal reflection. It's really useful. So let's do some math. Total internal reflection. Let's stay. So again, smaller than critical angle, there is still refracted beam. Exactly at critical angle, there is no refraction. Larger than critical angle, there is all reflection. So let's use the same equation. N1 sine theta 1 equal to N2 sine theta 2. And then one of the, well, yeah, there are two criteria or requirements for total internal reflection. One is the angle has to be larger than theta creds, critical angle. And what is N1 and N2? Which one is bigger? Timothy, which one is bigger? Okay, in 3, we should say Timothy. 1, 2, 3. Timothy. Oh, he's using his ear. Okay. Timothy, which one is bigger, N1 or N2? It's right there. Which one is bigger? N1 is bigger, right? Glass to water. So N1 is this first criteria. Second criteria is N1 larger than N2. Okay. You may wonder whether that thing is true or not. Let's say N1 is smaller. No matter how I bend the light, there is no total internal reflection. So it has to be larger. Okay. And then when theta 2 is 90 degrees, then we get theta cret. So theta cret is when theta 2 reach 90 degrees, and sine of 90 degrees. What is sine of 90 degree? You should know this. 1. Good. So we can just cross this. Okay. So that means sine theta cret is equal to N2 times 1 divided by N1. And again, remember, we need to check our derivation. Which one is bigger, N1 or N2? Timothy, sorry. Which one is bigger, N1 or N2? N1. So it's less than 1. Right? So there is an, but for the other condition that failed miserably, which is N2 is bigger than N1, then this number will be bigger than 1. And we know that sinusoidal function is bounded between +1 or -1 to +1. All right. So what have we learned today? We learned that lights travel along a path that takes the least amount of time. We learn about refraction. And we learn about something that is very useful, which is total internal reflection. All right. I'll see you on Friday.